Okay, so hello everybody. As Carlos says, I'm going to speak about how far is quantum search from quantum machine learning. This presentation is under construction. I mean, it's not the work I did during my PhD. It's the final months of my PhD and the initial months of my postdoc. As Carlos says, in this question, there are 3 points. First is how far a distance between two concepts, that is quantum search and quantum machine learning. During my PhD, I focused on quantum search because I didn't study physics as many of you. I studied computer science and I specialized, or my area was classical machine learning. And in particular, the quantum search applied to classical machine learning. So during my PhD, I moved from classical to quantum, but I continued doing search-related things. And what I did is I developed quantum search that I will explain what is, but always looking to quantum machine learning. So for me, it's very interesting the relationship or the distance between quantum search and quantum machine learning. And now that I can think that I understand something, not too much, but something about quantum search, I can try to apply or approach to quantum machine learning. So this talk is divided, or it will have two parts, quantum search and quantum machine learning, and I will try to answer how far are they. But sorry, I'm not going to answer because it's very difficult to understand. It's something that I'm doing right now. As a motivation, as an introduction, depending on your level, or I want to say how I understand artificial intelligence and machine learning, but very fast. We can understand an artificial intelligence algorithm as an autonomous algorithm that in unknown environments that something random things can happen, the agent or the algorithm try to understand what is happening, reason about the facts and act. It's a very generic definition, but it's enough to define artificial intelligence and machine learning. And the important thing, how the agent or the algorithm works in these unknown environments, is with a knowledge or learning model of the problem. With saying this, what I want to do is show the concepts or the names that I give to the things that sometimes could be different what you use, and sometimes I see this problem because when I say knowledge or learning model of the problem, it's something weird. Well, it's just the model that the algorithm constructs to work on the unknown environment. And how it does, which techniques? Well, artificial intelligence algorithms work with reasoning, inductive or the deductive. Mainly the machine learning algorithms are inductive reasoning. So is the reasoning that I want to use here. And inductive.
May I ask, what's the difference?
The difference is
inductive?
Yeah, if you have general cases and you want to extract, if you have many cases and you want to extract general knowledge, a general model is inductive. You are doing an induction process. If you have these rules and you want to apply to something, and from this data or model you want to understand something different, you have deductive. Is from concrete to general or from general to concrete. In machine learning, generalization is inductive reasoning. In artificial intelligence, in quantum search, or some kinds or sometimes of algorithm quantum search, it's deductive. The data that we are using in the artificial intelligence algorithms is big data, is large state space with high dimensionality, and the complexity. Many algorithms in artificial intelligence and machine learning belongs to NLP. At the end, it's just general. It's not. I will explain more concrete to the algorithm that I want to use. But if you see the typical plot. So in the relationship between artificial intelligence and machine learning is deep. And the application of salons. Okay, so in machine learning, we can have 3 different of of algorithms, supervised and reinforcement learning. Quantum machine learning focus mainly on supervised, so I'm going to focus in this talk on supervised learning, but something that they want to say is unsupervised learning and reinforcement learning are also important, very important in classical machine learning, and quantum machine learning didn't focus on this algorithm or didn't focus too much, and it's something that I would like to explore more. I mean, when I speak about quantum search and machine learning algorithms, here I'm going to focus on supervised learning, but during my research, I don't speak or don't think just about supervised, also unsupervised and reinforcement learning, mainly unsupervised and supervised. Okay, so, well, supervised, yesterday Elias spoke a little bit about that, but supervised learning can be defined as a set of data which its data has an input data and a label associated. So what you want to learn or your knowledge model has to find a function, maybe a function. It could be something different, but generally it's general enough to understand as a function that given data you has to infer the label or the label associated to this data. And some examples are support vector machines or artificial neural networks.
Sorry, and in few words, then in this language, what would be the reinforcement learning? I see the difference between the first two. I know you will talk about the first one, but this reinforcement learning would be...
Yeah, reinforcement learning usually is understood as an agent that is in an environment that the agent has to explore the environment. And the exploration is done executing random actions. Then once the agent has explored the whole environment, or at least enough quantity of action, it has a policy. And this policy determines which is the best action to execute once that you're in the state.
I think I've seen Sophia.
It's very, you can understand as a robot that is trying to learn how to interact with the environment. Okay, so if we understand the supervised machine learning, the limitation of machine learning is mainly time and precision, or we can summary as a time and precision, and you can speak about course of dimensionality. So once you increase the dimensionality of the data is sparse, so it's more difficult to clusterize them, to make the regression, etc., etc. So if we analyze the machine learning algorithms, we can understand that the two main points in which we want to improve the machine learning algorithms are execution time and precision. Execution time could be the time that you employ to generate the knowledge of the learning model, or it could be the inference part. But in general, in the classical machine learning, once you generate the knowledge model, it's very easy to infer the data. So everybody is focused on the training part. And then on the other hand, is on the precision. It's the accuracy of the model, the accuracy of the precision, the accuracy of the predictions of the model. The main problems related with times are the large training times, the trainability of the model. Sometimes the classical model are so complex, so big that to train them it takes, even some of them it takes months. It's very well known that ChatGPT takes a lot of time, energy consumption, even water. It's crazy how hard it is to train them. And the scalability. When I speak about the scalability, it's once the size of the input data, the size of the problem increases, how the complexity of keep executing this algorithm increases. Sometimes just increasing one unit in the size of the problem, the complexity of execution this algorithm scales exponentially. That is the reason of it belongs to P and P to other complexity classes. And the problems with the precision is the prediction error. Sometimes the classical machine learning algorithms predict something that is not accuracy, so it doesn't generalize very well because the knowledge model that is generated, it has some bias or some unknown error. And also the classical machine learners, where they are not too precise, it's because the transformation that it needs to execute or the transformation it needs to learn in the knowledge model is too difficult, or imagine that we have an artificial neural network algorithm, maybe the layers are not well defined or whatever, so we have problem with the expressivity. And the solutions that we usually do, it's parallelism. For the time, we parallelize all the algorithms in order to increase the efficiency, the speed up the training algorithms, or some other kind of improvements that people can do in the hardware or in the software part for the time. And for the precision, it's in order to increase the precision, they just increase the training times or they just include more data.
So that also very nicely ties together with what Elias said in his nice presentation. That's really basically adding on what he said, right? On Wednesday.
Exactly.
Nice.
It's exactly the same, but just in a more abstract level.
Yeah.
So why quantum machine learning? Well, if we have the limitations, we clearly understand the limitation, then try to improve everything with the quantum machine learning. And I take something that Maria Shu written in the paper in the supervised quantum machine learning models or kernel methods. What happens is we replace supervised machine learning with a quantum circuit. It's exactly what quantum machine learning tries to do. Mainly there are two ways of training the quantum machine models, that is kernel-based or variational training. Of course, there are more, and there are combinations, but just to show what I want to say to you, these examples are enough. So if we have this kind of training, what we have to do is to find a kernel or to find an ansatz or to define a hypothesis space, other things. What we want is exactly the same what we got with the classical algorithms. We have to focus in trainability, expressivity, generalization, and scalability that I already defined, but also we have to we have to very careful with classical simulability. Why? Because if our algorithm or our quantum machine learning model is too easy to simulate classically, it has no sense to use a quantum computer to do something that we can do very easily with a classical algorithm. So as a summary, while using quantum computing in machine learning, we can say time and precision, that we could try to work to get more generalization or better expressivity or improve scalability. And the quantum machine learning algorithm more used right now are the parameterized quantum circuit variational, that are not quantum neural networks, as Elias said yesterday. And I remember once that Marco Cerezo started a talk saying, okay, I'm going to speak about quantum neural network, but I just say quantum neural network because I want that all of you listen to me. Then now I'm going to say this is not a quantum neural network, this is a parameterized quantum circuit. And the other thing is quantum supervector machine, that at the end it's kernel methods. I don't know if you more or less know how it works, but the kernel method modify the dimensionality of the data, and it tries to classify using applying this kernel, and parameterized quantum circuits modify some parameters in a quantum circuit using a classical optimizer. Very, very fast. I don't know if you have any question here. Okay, we can continue. So what we observe, or what I observed, then it was the motivation part, the introduction part. Now I want to tell my story, to speak about what I see and what's I want to try to do. Of course, in quantum machine learning, there are some limitations, there are some problems. We observe some specific behaviors that makes very difficult to work on quantum machine learning. First is the Barren plateau, and with Barren plateau, there are a lot of different connections about exponential concentration and about trainability, but and there's a lot of work about that. But Barren plateaus start to prove that it's very difficult to work with parameterized quantum circuit. Also,
Yeah, or that is the wrong way of thinking about them, right? I mean,
yeah, it's
I mean, surely when you have like random initializations, you run into this problem. But I mean, I never know. I mean, it's very smart combination of warm starting and engineering circuits for the given instance might well overcome this problem completely.
Yeah,
Never mind.
Yeah, exactly. Maybe Barren plateau only saw that we have to do things in a different way. Then I started to interest on quantum backpropagation because I said, okay, maybe it's the easiest part is the more complex part for the classical algorithm. It takes a lot of time to do backpropagation, so maybe it's the easiest part to optimize, and I start to work on that. I start to think in different solutions. Then I spoke with Amir Abbas and other people in QTML in the CERN. And I realized that maybe quantum backpropagation is not the solution, or is not a good idea to work on that. So I also discarded. And then I read the double descent method, and I interested on that. But you published the paper like 10 days ago, so I'm still reading and thinking about that. But I think that is a very interesting proposal. So the conclusions that I extracted when I start to think about that, it's if we use gradient descent in a classical algorithm, or the problem of the gradient descent of a classical algorithm is that the landscape of the gradient descent is local. I mean, if you are in a point, in this point, you only can visualize what you have close to you, the neighbors. So maybe we can try to use quantum algorithms or quantum algorithms that can see the global landscape, that can try to do a global optimization, not just local, global, to see the whole state space. It's if we try to do this classically, it's brute force. Brute force classically is very bad, or it's the first algorithm that the people do in the 70s, because it's the fastest, if you think it's the simple way to do or to search. But of course, if you have to visit almost 90% of the state space, your algorithm is very, very slow, because you have to visit a lot of points in your state space. Classically, it was discarded, it was not very developed, but maybe quantumly we can try to do something different, because we can take advantage of the superposition and the interference between the states. So following these ideas, I reached the point of quantum search using quantum walks, and I started to think that we can think machine learning as a search. Classically, it is done. In fact, search is a basic point of optimization, and optimization is a basic point of machine learning. So I started to think, okay, classically we can see machine learning as a search. Maybe we can try to do the same quantumly. How it's how it's done in classical machine learning? Well, we understand what is a state space, that in this state space, I can try to find a point. I mean, we have the whole state space, and I know a point that has a concrete properties, or it's fulfill some restrictions, or I use a function and I get the minimum cost or the maximum reward point, whatever. But I have a state space and I want to find a point according to a function that I define. Also, we can understand a state space as a space that an agent needs to traverse. I mean, an agent that starts in an initial point needs to reach a final point. For example, always when I'm in Spain, I use the example of Madrid and Barcelona. If I want to go from Madrid to Barcelona, I have a starting point, I have a final point, so I have to search the best combination. Or also, I can think the state space and as the hypothesis space. I have a set of hypotheses. Different hypotheses are built with different, using different parts of the data, and I have to find the hypothesis that maximize the generalization or minimize the number of elements to build this hypothesis. For example, in the neural network, or if I try to construct a learning model to generalize something, if I have to classify fruits, I can say, okay, I can use the shape, the color, I can have a hypothesis that says, if the color is red and the shape is a circle, it's an apple. But if the color is yellow, it could be a banana or another fruit with a yellow color. This is a different hypothesis, and I can have a function that defines or classify the hypothesis, saying if it's good or not. It's if we try to visualize, it could be like a 3D, and a state space. It can be a 3D state space, or it could be a 2D. There are different state spaces. Of course, the dimensionality is much bigger than 3 or 2, but it's very useful to visualize it. So as I said, we can have a starting point, a final point. I have to search to find the way or the path to that minimize something. Or it has a function, the whole state space is characterized by a function, by an f of x, and I want to sample the state space to find this f of x, and I want to do with the minimum samples possible. So there's a lot of options. Or I have a hypothesis here, and I want the hypothesis that minimizes it.
Can you just ask, how should I think of this different? If you choose the agent interpretation, how's that different from reinforcement learning?
Yeah, the agent interpretation is exactly the reinforcement learning.
Okay, fair enough. Awesome.
Yeah, it's the behind of the reinforcement learning is an agent. It's a Markov decision process. It's a Markovian agent.
But then, I mean, there's the specific flavor of like this expected discounted rewards would be specific to reinforcement, like that you would not necessarily.
Exactly.
Okay, so reinforcement learning has a specific reward function that I should think. Okay.
Yeah, the reward function is not exactly the reward function you can think as the f of x, because the reward function takes into account other things. But yeah, the basis is a Markov agent, and then you modify.
Thank you.
And the point to use brute force quantum search or brute force is that the f of x, the function, cannot be defined or cannot be analyzed analytically, so it had to be done numerically with samples or whatever. So what is a search algorithm? Here I use the Markovian agent. It could be a set of state actions, the probability transition between or two actions, and the reward. That is exactly what you want to say. And the agent can start here and traverse the state space. Classically, there are or search algorithms are classified in uninformed and informed, what means that or the search is brute force and there's no anything that you know about the states, or it's informed. That means you have a previous knowledge about the domain or about the state space that you want to traverse, and you use this structure to do a more efficient search. and very good example of an informant is random walks, but there are others like death first search or bidirectional search, etc. And the weights you generate the successor randomly or just with a sequence, but without knowing anything of the state space that you are traversing. It's very fast generating the successor, but it requires exhaustive search, it's a brute force, or it has a path scalability. You can imagine a log with 3 numbers. You have to try one by one the numbers until you open the log, and there's no way to know if you are close or not to the solution, to the number that opened the logs. Maybe you are trying just one number difference with the solution and you don't know absolutely anything. So it's a exhaustive search, it's a brute force search. But if it's informed, it's different. You have some structure of the problem, you know something about the problem, and you can use it. A good example is Metropolis casting, but there are others: heuristic search, tabu search, min-max, whatever. I use Metropolis casting because I will explain the quantum version of the Metropolis casting. That is what we were using.
Okay, can I ask? Well, okay. I was about to say, can I ask a question, but actually, it's not the question. It's 3 meta mind maps that I can possibly share without derailing this. Can I do this?
Okay.
Because what you say is it's not about 2 things and it's about 1 thing, right? It's not about the following, because people are like, for example, also in optimization, people are much thinking about search attitudes in finding quantum advantage in optimization problems, like what Ronald de Wolf is doing. It's like very much fond of looking at polynomial advantages using Grover methods in optimization. I mean, you would even be reluctant to talk about any super polynomial advantages, because even if some instances can be much better solved quantumly, you would say, yeah, but that's a sub-problem, and you should rather talk about sub-problems than not hard. So he takes this kind of Grover attitude to optimization, which is reasonable. I mean, very reasonable, obviously. But that's not what you're doing, right? Second, there's in classical machine learning, there's also this kind of diffusion models or diffusion probability models that people look at as in generative modeling, where they set up like diffusion equations to generate samples of a type that has also a flavor of sampling out paths in machine learning, but that's also not what you're doing, right?
Okay.
And what is a bit related to what you're doing is to find better strategies to sample out local like regions around local optima in cost functions better quantumly than classically. That's more along the line that you are thinking about, correct?
Yes, but it's a little bit mixed with the first part, with the point 1. I mean, it's a little bit based on Grover, and as you will see, based on Grover, this part of the optimization is based on Grover, and then try to apply to find any advantage in the training part or in the generalization.
Okay, very good.
So, as I was saying, we started with quantum search based on Grover. The part that is interesting for us in the quantum, the Grover algorithm is just we have an operator applying over the initial state that it creates the superposition with some weights. These weights is the initial or the starting point are the weights that we are interested in. And also we use the reflection over the initial state, over the mean, over what we need. Using these 2 parts, it's useful for us. Well, Quantum Walk use this part, and then it's useful for us to build our own quantum algorithm, quantum search algorithm. The important part here is the advantage, as much it will be quadratic, and depending on the problem, it could be not so good, it will be just polynomial. And the limitations of using this quantum search algorithm based on Grover is we need or an oracle or a QRAM, but it's more an oracle. We use a QRAM just because we are trying to solve some big problems, and QRAM is very useful for us to avoid to calculate some things or to reduce the number of qubits, but it's based on Oracle. So we use discrete time quantum walks. It can be defined as we have an initial state, and we apply recursively. We apply many times an operator U until we reach a certain point. The initial state could be a superposition, could be a fixed point, could be a distribution around some point. I will explain in different examples, but it could be what we need. And the operator could be it's an evolution, but it could be different things. So we can define the initial state of the quantum walk just as a state and a coin. The coin, it's in 0 or 1, it's in a superposition, is the simplest quantum walk that we can define. It's a superposition up, down, as you prefer. And the initial state is also in a superposition that we define as we prefer. And it starts in the initial point, and after each step is this U operator, it starts to traverse to explore the state space. Mm-hmm. For example, in this case, it's just the coin is just a Hadamard, it's a bidimensional, so it's in a dimension each time that it's executed. This quantum walk was proposed. There are different authors that propose it, but it was started by Andrew Childs, and they started around 2000, but it was with Mario Szegedy that the quantum walk was formally proposed and was a little bit more useful. So Szegedy says that this U can be defined as a reflection operator and a sieve operator. The sieve means just that the coin, if the coin is in a 0, the Szegedy explaining the quantum walk as a line. In the middle of the line, you have the initial point. If the coin is in 0, you go to the right. If it's in 1, you go to the left. And just you are applying at each step, going to the left and to the right, and you traverse the whole state space. But of course, the coin can be something a little bit bigger. It's not just a bidimensional. You can imagine also like a dice or a bipartite graph, as Szegedy did. And you can replace this Hadamard in the coin by a swap operator that just exchange the state between them, or the probability of the states between them. So you can start in a whole superposition, a perfect superposition, and then you start to move between them according what you need. So as I said, Szegedy defined this U as a W because it's W from walk. So it's a step that you apply in your quantum walk is a operator W. And this operator W is defined with 2 reflections. And it's 2 reflections just because he decided to create a bipartite graph. So at the end, it's RS, reflection swap, reflection swap. But after Szegedy, it's proven that it's not necessary to use a bipartite graph as a coin. You can use something different, even you can simplify a lot. But it was the proposal that he did. So he changed the coin 0 or 1 by an n-dimensional coin, so by a bipartite graph. And the initial state is just a superposition. He put the state of each vertex. Each vertex was a point, then apply the reflection over this initial state, that is RR. Then he defined RB as a swap and reflection, as an exchange between G and I. So it started to exchange the vertex in the graph until it traversed the whole graph, or it affected all nodes in the graph. We take this all this quantum walks theory and we adapted to us because we didn't want to have an arbitrary coin. I mean, we don't want it to have a coin in which the transitions or the operation was previously defined. We want to use a coin related with this f of x that defines our state space. So we try to modify the coin and the whole quantum work, and we follow the Metropolis casting theory. If the classical Metropolis casting theory says that if a random walk I'm here and I have to move, I just randomly select a point and I move. And select randomly a point and I move. Metropolis casting, what it does is I select randomly a point, but instead of directly moving, I check. If I have an evaluation function and I have a value of each node, I compare both nodes, and if I, for example, I'm in a minimization problem, if I reduce the value of this f of x, if I reduce the energy, okay, I accept it, I move it, because it's interesting to me. If not, if it's increasing and I'm in a minimization problem, with some random probability, I traverse to the new state because I want to explore the whole state space, and I don't want to be stuck in local minima, because if this is a local minima, it's very difficult to escape from this local minima.
Because otherwise you would be doing just this greedy strategy, not
Exactly.
just always try to get,
Exactly.
want to explore.
Exactly.
Yes.
If not, it's a greedy strategy.
Do you reject sometimes places where you reduce the effects?
No, you always accept it.
I mean, there's more than one variant of quantum metropolis hastings, right? I mean, of course, metropolis hastings means that you have set up like a discrete Markov chain with detailed balance, and then when you go downhill, you always accept. When you go uphill, you accept with a Boltzmann weight, and then you can easily show that for long invocations of this, you will converge to the Gibbs state or so as the stationary state.
That's classical, right?
That's classical. Quantumly, there was this famous paper by Tobias, Frank, and others on quantum metropolis hasting. It was a wonderful paper that produced a nice idea and that had great results, except they were all wrong in a way. Although the ideas were perfectly right, but there was a little that mistake in the paper that was then fixed. So that's settled now, right? But that has settled been settled very recently, right? By Fernando and others. That's what you mean.
Exactly. It's
Okay.
very similar to this.
And this needs some sort of phase estimation, no? At some point.
No,
No, but
This
this
one.
paper of Frank and Tobias, there is phase
Yeah,
estimation. right?
I mean, of course, the way I said it was maybe not appropriate, because of course I have the fullest respect of this wonderful work. And yeah, I think the technical challenge is that in, metropolis sampling, you measure and then you accept or don't. And measuring is not an option in quantum mechanics. You do a kind of a soft measurements prescription, and then strike the right balance in learning something and doing something. And this is the tedious bit.
Mhm.
And that's where I think this comes in.
yeah, this is the key. We don't use quantum phase estimation. We have some operators to avoid that.
Mhm.
So the registers that we use to implement the quantum metropolis casting or the theories, we use four registers. The first register is the state register, just to represent the state space.
Before you move on, you said you always accept when the loss function goes down,
Yeah,
right? Then how is it different from a greedy strategy?
for them.
How is it different from a greedy strategy?
Yeah, in the greedy strategy, if the value is increased, you always reject. But with some probability, in metropolis casting, you accept it.
Okay,
The difference is in what you do when you reach a higher value.
Yeah, exactly.
I see. So with some randomness, you also reject good solutions in metropolis hastings. essentially.
Accept bad ones.
Except-
Yeah,
or
exactly.
The other way around, yeah.
Exactly. So for state registers, the first state register is just to represent the state space. Then movement register, it's a pointer, just deciding which register I'm going to move. And this movement register is important, it's key, because it defines if you want to exchange all points just with the first neighborhood, or with second, or it defines how you are going to traverse the state space. Then the coin register, that is not a binary coin, it's not a dice, it's not a bipartite graph, it's a register that can contain the results of the evaluation function, or can modify the state register using this evaluation function, and an ancillary register just to store the result of calculating the evaluation function over the register. You use an ancillary register, then you load the coin according to what you have, and you move the states. As definition, the state space, P are the possible movements, P is the coin probability, and the delta phi, the delta stores the difference between the actual states and the movement. And the acceptance probability, that is the key definition of metropolis castings. It's just we might minimize one, just to accept always that the evaluation function is minimized, or the exponential of beta. Beta is just an annealing schedule, and the difference. We can use this annealing schedule to, at the beginning, accept as much changes. It doesn't matter if the energy is increased or decreased, and then we modify this annealing schedule to avoid accept too many changes. But in fact, or in the practice, we realize that this annealing schedule doesn't work very well in the problem that we have, and we just delete it, we skip it. So the quantum metropolis casting that we define works with these operators. The V operator, it's just to create the superposition of all possible movements. Here I don't put, or I don't include the operator to create the initial state. It's just because sometimes we put calamars in the state space to create a uniform superposition. We just sometimes we are starting a fixing point. Just this is the doubling, so it doesn't depend on the initial state. We create the superposition of all possible movements. It's the same. It depends of how you decide that your state space is going to be moved. It stores the evaluation function calculated in the state register, store it in the ancillary registers. F, modify the coin, or load the coin, or modify the probability of the coin according to the results that we get of executing F function, and we store here, coin is modified, and then F apply these rotations to the state. And we inverse, and we apply the reflection over the whole state space. What we also observe is that these inversions are not so important, but is just to try to keep the same scheme that here. So this is the first reflection, and this is the rest of the operators. Reflection of the operators. So using this quantum metropolis, we built a quantum metropolis solver. It's just we built it just in order to try if what we are doing in the search is working or not. It's not very important. It's too many software, even classical parts here and here, and also here to compare things. The important thing is that what you see here, it's here. Okay, and we execute it. So what we want to solve with this QMS, it's what we define it as sample and search problems, or sample and search techniques. What we say is, we can try maybe here, it's easier. What we say is, we can take the whole state space, instead of sampling the whole state space, we can take a subset of this state space, sample it, get some results, whatever, and move to a different region of the state space in order to characterize the whole state space. Why we did it? It's just because we tried to solve some problems that the whole state space was too big and we need to make some tricks. But at the end, it's just an QMS is a software tool or it's an algorithm that can solve sample or search problem, independing how it's used. I will show different solutions. But what we saw is that this quantum metropolis casting or QMS performs a very good sampling task. How we can see? In the x-axis, we have the whole state space. It's a state space very, very small with just 2 qubits and with 2 registers and 2 qubits per register. So it's 16 states. It's not very big, but enough to visualize it. And here we have the amplitudes of the probabilities. And the black line is the function that we want to sample. Okay, so we try to sample as closer as possible this black line. If we execute our quantum walk with different number of W operators, we see that is very close to the black line. We also tried with the classical algorithm, and the lines were very far from the black line, just with 3-4 executions. But and I didn't include it because the important thing at the end is the quantum walk. But the important thing here is the quantum walk, or what we see, it's close.
I have to be so impolite to get power. Sorry, I just continue. I need electricity, otherwise I'm jumping out.
Can I ask a question about the algorithm?
Yeah.
One part in which you load the result of an evaluation function into another register. And just that part is what Jens also said, that, oh, it's the valuation of an energy that is the difficult part, and you either measure it or you do something else. And what you're doing is that you're saying that that's just unitary operation, that is something you can apply. And in general, you're completely correct. You can just apply this, but do you mention how to implement this? I would call it an oracle or an evaluation unitary.
Okay. No, I think that your question is how to apply this evaluation function in the state to Enzinas. Okay, this is a good question. We can see in the examples, but this evaluation function depends on the problem that you are solving. In general, this evaluation function is too big that we have to calculate classically and then use a QRAM to load these Ancilla states, okay? But it's just a trick that we did to try to simulate. We also did a different work, including a very simple evaluation function that it was just a restriction satisfaction problem. And how we implement with quantum operators, or we create a quantum operator implementing this f of x, we using taking as an input this state register in a superposition. We apply once this operator and we load this ancilla register, the solution of this f of x in a superposition in the ancilla register.
So to me, that sounds like if you know f, then you have to have some efficient implementation of this, I want to call it, or an evaluation function. And you do that by Taylor expanding your f, or I'm just thinking about how we do this in practice.
Yeah, it depends.
I mean, but if you have a classical algorithm that given x computes f of x,
Yeah.
then it's straightforward to create a quantum circuit that prepares sum over x of x f of x. You know, get x, get f of x.
I would love to see that.
I think this is a standard. If you have a classical decomposition of your computation of f of x in terms of and or not basic
then of
gates,
course, yes,
then,
yes.
yeah. But this is the case. No, if there is a classical efficient evaluation, means that there is a classical circuit of and or not, and then boom, this allows you to construct unitary that prepares that evaluates in superposition x f of x.
Amazing. That was exactly what I was asking for. Thank you.
Yeah, exactly. We have an example of that. We are working on that. It's a satisfaction restriction problem. But we didn't publish, and I didn't bring here. But it's, if you see the circuit, the whole circuit is super big circuit. Just to calculate the f of x is very, very complex. But we can we prove that we can do it. Okay, so as I said, it's samples. We observe that it's samples, and we also use a metric, a figure of merit to evaluate our algorithm. TTS is a metric that it's already proposed by other authors. We use it just in order to try to prove that it's working. It's not very relevant, it's not part of the science. I always say that it's more part of the engineering, because it's just a figure of merit to prove that what we are doing, it's better classically than quantumly. How we do it? We use this plot. In the y-axis we have the quantum TTS, in the x-axis we have the classical TTS. So if I have a point here, means that I have a low classical TTS. TTS means time to solution.
But I like to say, like, I mean, my wife tells me, "Can you bring A to school?" I say, "Who is A?" Alva, your only daughter. That's how I'm with abbreviations. So we lost.
Yeah, it's time to solution. So lower TTS, lower time to solution is better.
But
Okay.
what is delta and PT?
Okay, PT is the probability of measuring the goal state or the state.
Yeah.
And that is the confidence. It's 0.9. Okay, and this is the number of steps. So the TTS in the step 10 is whatever, 10 by this. So as I was saying, in the y-axis we have the quantum TTS, in the x-axis we have the classical TTS. So if I have a point here that is in the upper triangle, if it's here means low classical TTS, low time to execute an algorithm, so it's something good, and high quantum TTS, that is something bad. So if I have a point, an algorithm executing something that has a low classical TTS and a high quantum TTS is in the upper triangle, means that they have a classical advantage. It's faster, the classical, because the TTS is lower. And in the opposite way, if it's in the other triangle, it's a point that maybe it's here with a low quantum TTS, low time to execute the algorithm, and high classical TTS, high time to execute the solution. So in this triangle, we have the quantum advantage region. The important here is this diagonal, this gray line, that if something is below the diagonal, means it's quantum advantage region. It is over the gray line, it's classical advantage region. So you can have different cases. For example, if you have this case, mean that with the small sizes of the problem, the classical advantage is not very high, but when you increase the size of your problem, the advantage of the classical advantage is much higher. So it's something that you don't want to have. This is the best case. With the small sizes of the problem, you have better advantage than with big sizes of the problem, but it's difficult to have it because, of course, we don't have quantum advantage. The ideal one is this one. You have an initial classical advantage, but since you start to increase the size of your problem, you start to approach to the gray diagonal. And it's the case that we have. I will show. Also important, TTS is just a prediction. It's not a real execution time, because of course we execute our quantum algorithm in a quantum simulator running in a classical hardware, so it's impossible to have a quantum advantage.
Can I ask a question?
Yeah.
So this TTS metric, could you interpret that operationally, and why is this justified? Like this metric, or the goodness of this metric, rather? If you were to interpret this metric operationally, how would you do that?
The point here is you execute the same algorithm classically and quantumly. You measure the number of times that you apply the classical operator, because in the classical algorithm you can define this query complexity, and the number of times you execute these queries classically is the classical TTS. The number of times that you execute this quantum operator is the quantum TTS, and you compare.
It's the number of times you need to do it to find the right solution with a certain probability.
The number of queries you need to.
Exactly. At the end, it could be like a query complexity, a comparison between the classical and quantum.
Yeah, I think that it's kind of effectively that, no? Because if you assume that PT is somehow 1 minus 1 over T to a power, no, that this would be the case, no? The larger the T, that is an integer, you repeat this, this is 1 minus the probability, 1 over the probability. And if you do that here, there,
Yeah.
it's kind of a correct, it's like the number of times you do it, but with this logarithmic correction in terms of the probability of accept, because it's not the same like doing 20 times, but accept with probability 1 over 5, that do it 100, but accept with probability 1 over 3, that you are happy.
Yeah,
with this.
it's imagine you want to calculate the classical TTS for the step 5, so you have 5 and the probability. The difference is the probability which or the probability you measure classically is not measured, of course, but the probability that classically you get these the results and the probability you have quantum. So if you have quantum advantage using TTS means that the probability of measuring the quantum state is higher than the classical one. Okay, so we apply. Then now I'm going to explain very fast the application that we did of Quantum Metropolis Solver to optimization problems, to problems that are close to machine learning, and just to show that why we think that it is working. Applying to an optimization problem, it's applied to the protein folding problem. Protein folding, if you have the protein, this protein in our body has a 3D configuration, and this 3D is determined by the minimum energy. So a 3D configuration of a protein only survives in our body if it's this configuration, the 3D structure has minimum energy. So if you want to build artificially a protein, you need to create or you need to find this minimum energy 3D configuration. This is a very hard problem. In fact, very recently, the company DeepMind created AlphaFold using something different, machine learning with different techniques, and they won the Nobel Prize this year for inventing or creating AlphaFold. We try to do the same, but instead of using classical machine learning, using an optimization algorithm, a search algorithm. How? We started with the protein just as a line, and we searched the different configuration or the different rotation of the protein that minimize this energy. So at the end, the state space is all possible 3D configuration of the proteins, and the point that we are looking for is this configuration that minimize the energy. There are other approaches using quantum algorithms for protein folding, but all of these approaches are based on lattice models that are not very representative of the reality, because they assume 90 degrees connection between amino acids. That is something not realistic. So it's the same. We created a software architecture that is very similar to Quantum Metropolis Solver. At the end, it's Quantum Metropolis Solver adapted to Q4 problem. And we get this TTS plot, as I saw you in the previous one. With small proteins, we have this gap. With bigger proteins, we start to see that the gap was reduced. It's an optimization application of the quantum search. We also execute this quantum search algorithm, this Quantum Metropolis hashing, or the Quantum Metropolis Solver, as you prefer to call it, in hardware. And we saw that also, of course, we don't get the same results than in the simulator. But we say, okay, this red line is the noise level, and let's see if executing a couple of W's, we start to see some inference, and we see that we try with 8 proteins, and we see with 7 proteins, we start to see inference. Of course, it's not demonstrate that there is an advantage or something like that. It just demonstrates that our implementation of a quantum metropolis has a little bit of positive interference in the state that we need in our quantum hardware. We also apply Quantum Metropolis Solver to a n-queen problem. N-queen I don't know if you know it, but it's very well known. It's a variant of the chess. I have in an n by n chessboard n queens, and I have to place them as in a way that there are no attacks between them. For example, this is a valid configuration of the h queen. This is not, because there are two queens in the same diagonal and two queens in the same.
It's like a drastic barrier.
So
I think solving this, I think it's an big hard or something like this.
Yeah, but most of these combinatorial problems are NP hard, right?
exactly. So the idea here is to show that the state space can be represented in the same way. You can represent it as all possible configuration of the board. So you have to select the board that minimize the energy, and the energy, or the f of x, is defined as a penalization score, that if there are two queens attacking between them, you penalize them using the function that you want. The important thing is that n queen is very used as a testbed problem for some classical machine learning algorithms. So we try to show that we can do something similar.
Wait, but is this a counting problem? The problem is to see how many ways there are there to place the queens, or what is the problem?
No, the problem is just to find
Just one.
The configuration.
the configuration that there's no attacks. The point here is you have, depending on the number of queens that you select, you can have more than one solution. So our algorithm distribute the probability of measuring a solution between the n solutions. I don't know why this is here, but wow, it's do something weird. But classically, it's have been solved with different shards. We use this penalty function to find the configuration, the solution. The same, we plot it, we see that with the bigger instances are below the diagonal. And well, that's it was just the problem that we used to prove or to show how QMS was working. Then we apply QMS to Bayesian inference. And Bayesian inference, we understand it as by base formula, and we want to learn the posterior, having a prior, likelihood, and marginal. This likelihood is the f of x that defines the state space. The prior is some knowledge that we have previously about the problem, and posterior is what we want to find. And we apply this Bayesian inference, this sample and search to Bayesian inference to gravitational waves. Gravitational waves is just if you have two big black holes or neutron stars merging or orbiting one to the other, you are generating gravitational waves. So this gravitational wave can be measured here in Earth with two detectors that are 90 degrees, and when they detect the gravitational wave, they move and they create an interference pattern. This interference pattern is what you receive, then you need to analyze. And to analyze it, you have a set of parameters. The LIGO collaboration, that is the collaboration to study gravitational waves, they have 20 parameters to infer, and tuning this parameter, they try to fake, or they try to create artificially the same pattern that they receive. So if the pattern are close enough, they conclude that they find the parameter that define this event, this gravitational wave event. So we created a software tool again to try to work with LIGO people and show that maybe with our algorithm can find a speed up, because they have a problem. It's very, very slow to generate to calculate the likelihood of if it's possible configuration. So they takes too much time to analyze one event, and they have thousands of events. So it's a problem. So we create this software tool that is the same. In the core, the kernel of this software tool, it's the Metropolis, the quantum Metropolis casting algorithm. And again, we tested with TTS. We observed that with bigger sizes of the problem, that means more inferred parameters and more bigger discretization of each parameter, we get an advantage, or we start to get an advantage. But for us, it was not only important to have an advantage in time, we also want to have an advantage in accuracy. So we use this corner plot that is exactly the same tool that use LIGO people to have or to analyze the gravitational wave events. They have two parameters, in this case, just two parameters because it's easier to observe, and they have the inferred value with some variance. And what we observe is that the inferred value of the parameters that we get are just in the middle. That is exactly what they do. They do with 20 parameters. As much the maximum number of parameters that we can infer is 6. Of course, there's a difference, but we prove it that is faster quantumly than classical.
So, will it take too much to end? Just because we reached the soft deadline. So, if anyone wants to leave, you are free to. Okay.
Okay.
I mean, legally speaking, people are even, I mean, in principle, allowed to leave before.
Okay, and the importance of this problem is LIGO people not only want one point, they wanted to sample the whole state space. So it's not just they don't want just this point, they want the likelihood, they want the posterior, the probability around these points, because more dark color means more probability and then less probability. They get a distribution using sample answers. So just to fix, it's no more. The question that, as the beginning I said, is under construction is something that I'm working right now. It's can QMS or quantum metropolis casting, or what I know about quantum search, be applied to a quantum machine learning? I don't know. What I think that it could be interesting is this global search property, or instead of gradient descent, we can use this. We avoid barren plateaus with this global search. Let's see. But of course, it has some limitation. The quantum search that I know, the quantum walks or the quantum metropolis casting, is that it's a more complex algorithm than the gradient descent that works very well classically, and the upper bound in the advantage is quadratic. We are working to try to modify to get something better than quadratic, but it's not easy. And what I don't know is how far it's quantum search from quantum machine learning. I don't know. What I'm trying to do, or to close the gap, or to apply quantum search to quantum machine learning, is to find the best reward cost function state. That state can be a parameter configuration for a given f of x. It can be in the loss function, or it can be in something different. How I represent the state space, the hypothesis space, I don't know, but it's something that I'm trying to answer now. Other applications of quantum machine learning of quantum search to quantum machine learning will be Bayesian inference, or the other day speaking with Elias, he suggests me Bayesian neural networks. Try to represent hypothesis space in a different way are the future steps. And just to finish a little bit of publish, my group is a GICC group of information and quantum computing. Miguel Ángel Martín Delgado is our IP. And Angel Rivas is another professor in the group. He's working in open quantum systems. We have 5 PhD students, but working on quantum search, we are Sergio, Gabriel, Sarah a little bit, and me, that I'm a postdoc, and there are other 3 postdocs. They are working on open quantum system, and Kornikar is starting to work on quantum computing. And we focus on quantum algorithms, quantum artificial intelligence, not just quantum machine learning or supervised learning in general, quantum artificial intelligence, and fault-tolerant quantum computation, because Miguel Angel was an expert on that. And the other part is what Angel, Nacho, and Sagnik are doing, that is open quantum system. And about me, what I'm interested is try to use quantum search to improve trainability. I was focused on trainability, try to understand if we can train better to train better quantum machine learning algorithm, but I don't know. Also about the scalability. Trainability and scalability are my main focus, but I'm open to other things like generalization or outside of quantum machine learning to find just more general QI algorithms, try to find something beyond Grover in quantum search or other application of quantum search. If you want to contact me, this is my email and my GitHub. GitHub, we have all code that we have done during my PhD in the group, QMS, Quantum Metropolis Solver, and also we have another chemistry tools about that is called Fermion. And that's all. Thank you very much.
Anyone wants to make any question?
We had lots of questions along the way, but I'm sure there's more.
Maybe one maybe naive question. So I want to understand if I understood correctly the connection between the sampling problem and the searching problem, because I mean you showed that you solved somehow in the end sampling from some distribution.
Yeah, if you sample very well a distribution, there is 2 connections. If you sample very well the distribution, it's easier to search. Okay, if I can prove that if Metropolis has been sampled very well, instead of using the acceptance formula that I wrote it here. If I modify this, instead of sampling, I can do a search. So instead of mimic this f of x, what I can do is increase a lot the probability in the maximum or the minimum points.
So again, you want to sample from a distribution which is very big in the solution of your search, and you do this by using this Boltzmann.
Exactly. The difference.
So there is nothing really quantum in this choice, right?
Well, it's quantum because we use this acceptance probability that we include in the quantum algorithm. So
sure, no, I mean the steps and so on, that's the quantum part, but the function.
The function, yeah, it's not. And we also, I explained sample and search that for Bayesian inference, this sample and search here, we sample a region of the state space, we get some results about that, then we search a different region of the state space and we sample again. It's an iterative process.
Right, but in a fully QML type scenario, then the function that you want to optimize, this loss function in the end, is not a classically efficient function of your parameters, right?
Yeah,
it's to be something more complicated. So this would also not be clear exactly how to treat this.
Exactly. Yeah, it's exactly. It's not very clear to me.
No, very nice, very nice. No, it's super nice. Like overlapping with some ideas that have been floating around, but not in this precise flavor. That's very, very nice. And like, I mean, like, can you say more about like what proven separations one can hope for, like of quantum versus classical, of sorry, like of what proven separations one can hope for, like for quantum advantages, like what's in store?
But you mean using a search algorithm or in a problem, or
Using the search algorithm.
which could be a good separation between one or the other?
No. I mean, this absolutely comparing what you describe, and I know that quantum advantage is not everything to everything. I mean, yeah, but still, it would be good to see like what could be kind of proven about this in a rigorous fashion.
Yeah, I have no any proof of in which point it could be a quantum advantage, but what I'm trying to show, or how the first try that we think, the first thing that we tried, it was to try to optimize the selection of the parameters in a parameterized quantum circuit using a quantum search algorithm. But but we thought that it was a good idea, but we didn't find anything.
Okay. Wonderful.
Okay.
Any more questions?
I have a question.
Yeah.
QBER, does LIGO actually use QBER? I'm just curious, like at this level, there's a software package that does a classical simulation of quantum circuit.
Yeah. LIGO is not using yet. What we are doing with them is they have different samples. One sample is dynasty, whatever, but all of them classically. They want to include QBER as an extra sample and to run it in a quantum hardware, they pass everything and run in a quantum hardware. But it's something that we are speaking about with them, but they need proofs that it works, and we are not yet. Quantum hardware is not ready yet.
No, sure. Okay.
Okay, then let's thank the speaker again.
Wonderful.